How is it going, ladies and gentlemen? This is the Wolf around, and it's great to see you here. In this video, we'll configure our Vulkan Game Engine project for cross-platform development, starting with Windows. This is an important video because we'll be establishing a strong foundation for our game engine code. Subscribe to the channel, join the pack, you are always welcome here. Without further ado, let's get started. Before configuring a programming project, we need a useful code editor. In this video, I'll show you how to configure a C++ CMake project in VSCode. CMake is a build automation tool that makes things easier, especially in cross-platform C++ development. I'll use CMake to configure the project throughout this cross-platform Vulkan Game Engine series. Before starting the configuration, let me emphasize that VSCode will follow the CMake configuration we create. Now let's inspect the project folder that I've already created. I named it YT Vulkan Game Engine. I created a folder named include for the header files. I created a folder named source for the source files. I also created CMakePresets.json and CMakeLists.txt files, which I'll explain in more detail later in this video. Now let's create a folder for the third-party libraries we'll use throughout the series. I'll name it Third Parties. Important warning: in the previous videos, I demonstrated how to compile all the dependencies we'll use here from source. In other words, I'll be using the libraries that I compiled in those videos. If you followed the previous videos, you should have compiled the same libraries you see here on the left window. To configure this Vulkan Game Engine project, you need to watch the previous videos. If you haven't, there is a link to playlist in the video description. The first dependency I'll place here is GLFW. I'll create a folder named GLFW. Inside it, I'll create a folder named Windows. Inside the Windows folder, I'll create a folder named Include. I'll place the GLFW header files inside the Include folder. Next, I'll create a folder named lib inside the Windows folder. Inside the lib folder, I'll create two folders, Debug and Release, to store GLFW's libraries compiled for debug and release configurations. I compiled GLFW as static libraries. Using static libraries provides faster compile times and smaller binaries. First, I'll place the debug version of GLFW. Then, I'll place the release version of GLFW. GLFW is complete. Now I'll create a folder for GLM. I'll name it GLM. Inside it, I'll create a folder named Windows. Inside the Windows folder, I'll create a folder named Include. I'll place the GLM header files inside the Include folder. Let's navigate to the GLM source code folder and copy the folder named GLM into the Include folder. After pasting it, go inside the copied GLM folder and delete the CMakeLists.txt file located there. Next, I'll create a folder named lib inside Windows folder. Inside the lib folder, I'll create two folders, Debug and Release, to store GLM's libraries compiled for debug and release configurations. GLM is complete. Now I'll create a folder for SDB image. SDB image is a header-only library used to read and load image files. I'll create a folder named SDB image. Inside it, I'll create a folder named include. Let's head over to the GitHub page for the SDB image.h file and download it into the include folder. SDB image is complete. Now I'll create a folder for TinyObjLoader. TinyObjLoader is a header-only library used to read and load 3D model files in OBJ format. I'll create a folder named TinyObjLoader. Inside it, I'll create a folder named include. Let's head over to the GitHub page for TinyObjLoader.h file and download it into the include folder. You can find the links in the video description. TinyObjLoader is complete. Now I'll create a folder for GLSLC. I'll name it GLSLC. We'll use GLSLC to compile the first shaders of the series. Inside the GLSLC folder, I'll create a folder named Windows. I'll copy the GLSLC exe file into the Windows folder. GLSLC is complete. Now I'll create a folder for the Vulkan libraries we'll use. I'll create a folder named Vulkan. Inside the Vulkan folder, I'll create a folder named Vulkan Loader. Inside the Vulkan Loader, I'll create a folder named Windows. Inside the Windows folder, first I'll create a folder named include. I'll place the Vulkan header files inside the include folder. Next, I'll create a folder named lib inside the Windows folder. I'll copy the Vulkan1 lib file into the lib folder. The Vulkan1 lib file will link to the Vulkan1 DLL file at runtime, which is located under the Windows folder of your system. When developing a Vulkan application, you only need to link against Vulkan1 lib during the build process. This static library is an import library that allows your application to interface with the Vulkan loader, Vulkan1 DLL file at runtime. Let's head over to the Windows folder under the C drive and search for Vulkan1 DLL. There may be multiple Vulkan1 DLL files here, but only one will be loaded at runtime depending on your system's configuration. You don't have to worry about which Vulkan1 DLL will be loaded. But one thing you must ensure is that your GPU drivers are installed properly. Let me head over my NVIDIA drivers Vulkan implementation folder. Here, I'll check my GPU's ICD file for Vulkan. ICD stands for Installable Client Driver, and this file named mvvk64.json guides Vulkan-based application to the correct driver implementation. Of course, this file could be named differently if I were using an AMD or Intel GPU right now, such as AMD ICD64.json or Intel ICD X64.json. To summarize, the Vulkan loader, Vulkan1 DLL, will use the ICD files to load the appropriate GPU-specific Vulkan driver. Ensure that your GPU drivers are installed correctly so that the ICD files point to the valid driver implementations. All you need to do is install your GPU drivers. The Vulkan loader is complete. I'll create a folder named Vulkan Layers. Inside the Vulkan Layers, I'll create a folder named Windows. Next, I'll copy the VK layer Kronos validation DLL and JSON files into the Windows folder. We'll load validation layers only for debug builds at runtime in future videos. After copying them, open the JSON file and check if the library path variable is indicating the current directory with the .2 notation. If it is, everything is as expected. Vulkan validation layers are complete. Now we can start configuring the CMake files. The first thing you need to do is install C Cplusplus extension pack in VSCode. This package includes C++ IntelliSense and CMake management extensions. Search for it in the Extensions tab and install it in VSCode. After installing the extension pack, create a file named CMakePresets.json and fill it as you see here. This file works seamlessly with the CMake extensions installed alongside the C Cplusplus extension pack. Before going any further, let me remind you that either Visual Studio or build tools for Visual Studio must already be installed on your system. Installing one of these will provide you with Microsoft C++ compiler and a robust development environment. Even in this CMakePresets.json file, we indicate CL as the compiler. CL is the name of the Microsoft's C compiler. Now pay attention to the generator variable here. It says Ninja. The Ninja CMake generator is installed when you install either Visual Studio or the build tools for Visual Studio. The CMake extensions in VS Code will detect and use it automatically. Next, create a file named CMakeLists.txt. I've already created it, and I'll explain it now while highlighting relevant lines. You can fill out your own CMakeList.txt file as I explain it. Specifies that the minimum required version of the CMake to process this file is 3.25. If the user's CMake version is older, an error will occur. Defines the build configurations available for the project, Debug and Release. These are typically used to differentiate between development and production builds. Declares the name of the project as Vulkan Game Engine. This sets up variables like project name, which can be used later in the script. Specifies that the project uses the C++17 standard. This ensures compatibility with the modern C++ features. If the editor build variable is defined, it configures the output directory for executables. The executable files will be placed in a subdirectory named after the current build type, debug or release. Separate variables are set for the debug and release configurations to ensure proper organization. Editor build is a cached variable that I defined. Some cached variables are predefined by CMake, such as CMake CXX compiler or CMake runtime output directory. CMake runtime output directory determines where the compiled binaries will be located. I used both my editor build variable and the CMake runtime output directory variable to manage the behavior of the CMakeList.txt. If I am compiling my project in VS Code, the runtime output directory will be build out folder inside the project folder. Sets up the release build completion flags for Microsoft C++ compiler. MP enables multiprocessor completion. O2 optimizes the code for speed. MD links against the multi-threaded runtime library. ArcAVX2 enables AVX2 instruction set for better performance. Before using this flag, check if your CPU supports it. You can use a software like CPU-Z to check the supported SIMD instruction sets. If your CPU does not support AVX2, you can consider using SSE 4.2. It is supported by a wide range of CPUs. Enabling an SIMD instruction set is important because we'll often deal with the vector and matrix operations. By enabling SIMD, these operations can be executed much faster, significantly improving performance in computationally intensive applications like game engines. Sets up the debug build compilation flags for Microsoft C++ compiler. MP enables multiprocessor completion. OD disables optimization for easier debugging. MDD links against the debug multithreaded runtime library. Defines two variables. Workspace dir points to the root directory of the project. Third-party folder points to the directory containing third-party dependencies. Adds include paths for the following libraries: STB image, a single header library for image loading; TinyObj loader, a single header library for loading OBJ files. When compiling on Windows using Microsoft C++ compiler, additional platform-specific configurations are applied. Include directories for GLFW, GLM, and Vulkan are added. Library directories for these dependencies are specified with separate paths for debug and release builds. The Vulkan target variable is set to Vulkan1, representing the Vulkan loader's import library. Defines variables for linking against GLFW and GLM libraries. Adds preprocessor definitions. GLM enable experimental macro enables experimental features in GLM. This means that every translation unit, in other words, every source file in the project, will have this macro defined during compilation. Defines the executable target. The name of executable is the same as the project name, Vulkan Game Engine. The source file is located workspace dir source main CPP. Links the executable with the following libraries: GLFW, GLM, and Vulkan. Now press Ctrl+Shift+P and type CMake select configure preset. The presets we defined in the CMakePresets.json file will be listed here. Choose Debug MSVC. Next, press Ctrl+Shift+P again and type CMake configure. You will see the build dir and build alt folders created as we described in the CMakePresets.json file using the editor build and CMake runtime output directory cached variables. I just want to show you something. Let's delete the build dir and build alt folders and navigate back to the CMakePresets.json file. Let's change the generator to Visual Studio 17. And press Ctrl+Shift+P to configure again. You'll see the content of the builder folder has changed. You can use Visual Studio itself as a project generator in your CMake configurations as well. Since Ninja is my favorite, I'll switch back to it. Configuration is complete. Now let's run the project using the arrow-shaped run button below. In main CPP, I'll create two integer variables and set a breakpoint to test debugging. Debug the code using the bug-shaped debug button below. Now let's switch to the release configuration. Press Ctrl+Shift+P and type CMake select configure preset. Choose release MSVC. Run it using the arrow-shaped run button. I'm a software engineer specializing in computer graphics, game development, GPU hardware acceleration, AI inference, and cross-platform C++ development. I look forward to sharing more insights with you. Please like, subscribe, and leave a comment. I'll see you in the next one.